Good morning, dear. Welcome back. Today, we are going to discuss one of the most important tools in machine learning, that is the gradient descent algorithm, and we'll start its application first with linear regression model. Okay. In fact, this is the first algorithmic tool which you are going to learn, because so far whatever you have learned, those are analytical tool. For example, the normal equation in matrix form, all were great, formula based, and there was no iteration, but perhaps no iterations were here inherently in actually inverting the matrix, but other than that it was formula based. And as an engineer, you will have to decide when to use what tool. For example, if the number of features are not that great, maybe 10, 100, 1000, even 10,000, 15,000, okay, you can use normal equations, okay, because that will be quicker and that will be much more computationally efficient. But what if the number of features are great, means in the range of 100,000, few 100,000, so in that case the tool which I am going to discuss today will be useful, okay. That is the algorithmic tool, which is very popularly known as gradient descent algorithm. And this tool, with this tool, you will learn the algorithmic way of solving linear regression problem. But before that, let us take you to a tool. The optimization is the heart of all engineering, as you know, and although gradient descent is especially suitable for our machine learning application, in particular the linear regression, but other gradient based optimization, there was a subject in fact, that gradient based optimization, okay, where people used to optimize engineering problems, various engineering problems. It could be minimization, it could be maximization, using gradient method. It's a very powerful method, okay, but iterative in nature. Just if you Google it, gradient descent and images, you will get a lot of illustrative figures. I am trying to tell you about this particular figure. What is this? It is depicting, suppose these are the two variables. In our case, these are the two features, and this is an objective function, okay. In our case, it is cost function, okay. Now, in general, the cost function could be not in particular linear regression. Cost function could be having both maximum and minimum, okay. That's why the concept of local optima, global optima comes, okay. In these cases, there is no global optima, and the gradient descent algorithm essentially works like this. You can start from any initial value of these variables. Here the parameters, okay. Here the parameters, not features, sorry, parameters attached to the features, because we are going to tune those parameters. So you can start from anywhere, and we should be able to write the arbitration rule in such a way that it will slowly go down to this nearest optimum position. For example, if you start from here, it should be coming to this local minima. If somebody is running algorithm starting from initial values from here, it should be able to slowly come down to this local optimum, okay. So this is the general case, right, where you have local optima. But fortunately, in our case, case, I will show you that it will be always like this. Objective function will be like this because it is convex in nature, as I told you, and you have experienced it, right? With one feature, with one parameter JW by hand you have done, and you got a curve like this, okay? And with two parameters you will get a curve like this, and this will essentially have one and only one optimum value. Here it is minimum value. That's why it is called global minima. Okay. So in our linear regression algorithm, we will try to figure out where the global minimum point lies. That means how to tune these values or the parameter values so that irrespective of wherever we are starting, it will come down to the global minimum point. Okay. I will also try to show you a bowl set. If it is here, yes, go ahead. 3D, lots of images you can see. Yeah, so you see, this is the 3D representation of this. This would be our cost function, and one parameter, another parameter. Okay, and when we run the updation rule or the linear regression algorithm, then we would like to see how the algorithm is actually performing. That means how fast it is going to the global minimum. That can be done by plotting contour. So contour plot. So what is contour plot? So this is actually contour plot. How the plot is to be made, because we will use the contour plot while discussing the algorithm throughout the machine learning courses. Say you have this 3D object. Okay, this is the objective function in 3 dimensions when you have two parameters, and consider a plane perpendicular to the plane of the board. Okay, and go ahead and dissecting this 3D board, right? And project after dissection the top view you can see, and whatever is there you project it in this plane. Okay, and then you will get this elliptical type of curve, which is known as contour plot. Okay, and go ahead and I will show you. This is the contour. Yes. So suppose this is our two parameters W0, W1, and essentially we will get this kind of plot which is called contour plot. And contour plot is coming from here, as I discussed. And then you can see how your algorithm is running iteratively. This is my point, this destination, because this is the minimum value, right? So contour plot can give you this kind of visualization of how the algorithm is performing. Okay, then you can just switch on. So we will now, having said about this basic, showing some picture and telling you about the basics of gradient based method, we are trying to focus on linear regression algorithm. Linear regression algorithm. Okay. So here what we have the cost function which we have defined like this. Okay, and by very nature of this square, that is the quadratic nature of this function is giving you the global minimum. So this is our cost function or objective function, we need to differentiate this function with respect to parameters. And same thing we did for analytical methods also, and we equated it equal to 0 to get the equations which will determine W parameters. But here we will not do that. Instead, iteratively we will try to figure out what this means when that means I will have to differentiate this function. And let us consider first for one example, for one sample, JW will be of H Wx minus y square, where HW x equals to W0 x0 plus W1 x1 plus W2 x2 Wn xn. This can be written in vector form x, okay, where W equals to it is defined in the frame space n plus 1, and similarly x is also equals to n within space n plus 1. Okay, and I need to differentiate this function. Okay, let us make a substitution. Okay, so this is by substitution, we are just substituting s equals to this, so that JW now half a square. Okay, now you understand why half will be written. Okay, so now you are we need to differentiate this function with respect to W. I have made a substitution, s equals to this. Okay, and this is actually can be written as W transpose x. Okay, and I am differentiating this partial differentiation of j with respect to s and partial differentiation of s with respect to the parameter, and definitely this equals to 2 to cancels out s, and this is equals to x, and then the partial differentiation of the cost function with respect to the parameter becomes this. This is very, very important. Now in vector form we have written like this, right? Now you can write, okay, for a single parameter, say Wj, okay, that means the Wj attached with a feature xj. Okay, what will be? This will be W x minus y times xj, okay, and so on and so forth. Okay. So W, that j could be 0, 1, 2, 3 up to 10 is the feature. Okay. So that ensures that this also we are keeping in the gradient descent loop to evaluate each and every parameter will be evaluated through a updation rule whose derivative part is like this. Okay. Now let us try to write down the updation rule. Wj assigned to a value of Wj earlier minus alpha so this is the aberration rule which we are writing, okay, so that parameter will be evaluated. Okay, so this is actually not equals to, as all of you know in programming, right? So your assignment statement. So we can start from any W, right? Let us try to make you understand. Say I have a parameter here and I have a cost function like this. Okay, so this is actually the global minima where I need to reach. Okay, for that somebody can start from here. Say this is the initial value. Somebody can start from here, or her the initial value will be like this. Okay, and what is this? The derivative is actually tangent at that point. Here also if you try to figure out, now suppose you are here, okay, so derivative, since this is obtuse angle, so this part is negative definite, okay, and multiplied by an alpha. What is alpha? Alpha is known as learning rate. Learning rate. Again, it is a machine learning term. It has nothing to do with learning. Actually, this is controlling how this value will be added or subtracted with this parameter. Very, very important part it is playing. Normally, this value is empirically people has figure out the value 0.01, small value, and what small value and large value will do, you can see. Say this is my objective function. This is actually my step length. If I am this very small value means I am my step means W1 I am upgrading with very, very small step. So my computation will be large to reach to this point. Okay, but it will make sure that I will not miss this point. Okay. On the contrary, if somebody is making learning rate large, so your step length will be bigger. Okay, like that you can even miss this point. Okay, so carefully you will. So this is a control. Okay, that how will be my step length so that I will not miss this global minimum value. Now let us see. So you are now with me that this is by virtue of this minus sign. So wherever if it is in this zone of W1, it will be attracted towards this because this will be negative definite, negative and negative. This is a constant term, negative, negative, positive. So this value will be positively incremented and it will move towards this. Okay. So as the iteration will move on, it will move in this direction. On the contrary, if somebody is taking the initial value here, since this is positive definite acute angle, so tangent is positive, so this term will be positive definite and then this value will be decremented slowly as the iteration will be performed and will be moved toward this point. So this is a fixed point attractor. Wherever you are on this curve, here or here, so you will have to trickle down. The rule is formulated in such a way, you will be trickled down towards the global minimum, right? So that is the aberration rule for gradient descent algorithm. Okay. This is the most important, okay? So this is gradient descent. operation rule. Okay. Now, if for some reason, and as I told, engineers need optimization where sometime I need to minimize, sometime I need to maximize. For example, if my cost function is say profit function, right? Definitely, and still it is convex quadratic in nature. Definitely, the shape of my curve will be like this because I will try to maximize my profit. Okay, or if some reward function, J is representing reward function, then I will try to maximize the reward. So, in that case, the problem which we need to solve is known as gradient ascent. Okay, gradient ascent. So, what will be the updation rule in that case? Just I need to put a positive sign here. The same old story. Suppose somebody started from here with this initial value. Okay, so this is positive, so this is positive definite. So this parameter will be incremented and attracted towards W1. And on the contrary, if somebody is has taken an initial value here, and this will be negative definite, so some value will be eliminated from here, reduced from here, and slowly this will be again attracted towards this. So this again remains a fixed point attractor by simply changing the algorithm's updation rule. Okay. So this is very important thing to note down, and I will just show you that in terms of sample, our GD, gradient descent algorithm, in terms of sample, this is for one sample, right? Now, how to write it for m number of samples? Alpha, okay, minus y into xj from here. I'm just copying. Okay. So this term I have now replaced by this here, and then for m number of samples now, alpha, and for m number of samples, each step, for m number of samples, each step will be operated like this, and again for convenience I will divide it by m, and this will be my updation rule as my samples are given. Using those samples, I will update my rules, update my parameter using this rule, and you can see say I have it's like this. These are my samples, and I am starting say this is my hypothesis. Okay, and this is my, so these are my samples given, right? So normally initial values are, you can take 0. Okay, so this is 0, this is 0, means HW is 0, it is starting from somewhere here. Okay, and then slowly, okay, as this parameter will be updated, and remember, I need a updation rule for this parameter. I need another updation rule, means another loop I will have to run for this parameter. So as many parameters are there, that many updation rule I will formulate, and I will run the algorithm, and slowly when it will converge, my predictor will come here. Okay, this will be. So now, how do I know that it has converged? Okay, here the again and again I am telling, because my function, cost function JW, okay, is convex in nature. Wherever I start, it will trickle down here. Means I will reach to a parameter value which not change anymore. Okay. For example, let you start from here or here, but as soon as you reach nearer to this, there will be no substantial change. Okay. One more thing, you see, we have formulated this problem in such a way that I am not evaluating this, but it is good idea to evaluate this function also. Why? Because it will tell you that you are not going further down the line. Okay, because whatever parameter value is being refined in the process of running the iteration, always JW has to decrease. Okay, for example, in one step of iteration, JW has some value here for this parameter, right? Next time, for this parameter change, we will allow those parameter change only which will decrease my JW1 value, right? And that will ensure that wherever you start, slowly, the hypothesis function will be actually fitted over there. And where I will stop the algorithm when this is no more changing. Okay, with those parameters I will fix. So that will be my hypothesis. Okay, so that's all I wanted to communicate to you, the background of the convex optimization problem in very simple language we try to formulate. And in the next lecture, just methodically I'll formulate the different kinds of gradient descent algorithm. Okay, thank you for your attention. Stay safe.